Hi everyone, I'm Jim White, and this video is about is it possible to use carbon steel plates instead of stainless steel plates in a HHO generator. And before going on, I want to point out that HHO gas is very hazardous. The actual technical term for it is oxyhydrogen gas, but it's also referred to as HHO or brown gas. And this gas is very explosive. It's a mixture of hydrogen and oxygen in the perfect constituents to burn and give off an explosion. Oxyhydrogen explodes at 2800 degrees C or 5100 degrees F to form superheated steam. In fact, it's incandescent steam. It's a brilliant white flash. And shortly after the explosion, all the water vapor formed will condense down into water, and that's an implosion. So first you get an explosion, and then a huge vacuum is formed, and you get an implosion. And it's a tremendous producer of sound waves. You can lose your hearing permanently if this explosion or implosion occurs if you're not wearing hearing protection. So do not mess with this stuff. It's highly dangerous. Okay, here's my materials to start with. This is a 12-inch by 24-inch piece of low-carbon steel. I purchased some of these from McMaster.com, and they were $11.20 per sheet. And from that I cut some 6-inch by 6-inch plates, so they're about $1.40 each at this point. And two were made a little different. These will be the end plates, and the little tab is for the electrical connection. And this piece is a little smaller than the others, and I'm going to use that as a template to cut out the rubber gasket, which is 1/16 inch thick neoprene rubber. And this is just plain old carbon steel. As you can see, it's magnetic. And if you watched part one of these two videos, you saw how this did seem to hold up with a caustic electrolyte solution. So after I get some holes drilled and some gaskets cut, I'll show you a little more. Here's a bunch of gaskets that I've already made, and this is the way I do it. Just line up the template by eye. And then I clamp it in place, and I cut around the template with the X-Acto knife. Okay. There's that's my last gasket. So I have enough here to do 10 plates plus seals for the ends. Okay, here is the finished cell assembly. It's mounted on the corner and so that the bubbles can funnel up towards the exhaust port. So this is the electrolyte intake port, and then bubbles and electrolyte will come out here. So there's the plates with the rubber gaskets in between them. And we have 2 intake ports, one on each side, and 2 exhaust ports, one on each side. Here's the cell temporarily connected to the electrolyte reservoir. In here is a coalescing filter to keep bubbles from going down the tube to the bubbler. This is the fill port, and this tube will feed the bubbler. So there's 2 hoses from the reservoir to the bottom of the cell, and then 2 hoses back to the reservoir. So the gas should travel through these tubes and up the reservoir. I've added the bubbler to the system. That's the tube that's off to the right a little bit. At the bottom are 4 aquarium air stones to make as small bubbles as possible. So the output from the electrolyte reservoir comes down and feeds the bubbler at the bottom. And again, we have a coalescing filter to keep bubbles and splashing out of the exhaust fitting and tubing. So I just put a short piece of tubing to show you where the output of this system will be. Well, here's the setup of the HHO generator with the carbon steel plates. I have a power supply there on the left. Then here's the dry cell with 10 plates. And the tube on the left has the caustic electrolyte in it. The tube on the right is the bubbler. And then the output tube right now is going into that glass jar with water. Now I found that I've overfilled it. If you can see it, there's a black mark there where the top of the electrolyte is. And when I turn on the power supply, you'll see the water level rise because of the amount displaced by the bubbles. And I hadn't considered that initially. So we'll have to run at a lower power until we use up some of the electrolyte. Here, I'm going to turn the power supply on now. And you can see the level rising as we start to get bubbles. Now we're at 20 volts and 2.5 amps. And I'll have to run it like that for a while until we turn some of the water in the electrolyte into gas. After running the unit most of yesterday, we can see how much water we've used, and the black mark is the electrolyte level when we started, And this is the level this morning with everything at room temperature. Now we can see discoloration, but I think this is just like in the jar in part one. In the part one video, there was this color on the inside surface of the jar, but the electrolyte itself was still clear. And I think you can see this is a coating on the inside of the clear PVC pipe. Now down at the bottom, you can see some of this material, whatever it is, has collected. And I tested that with a strong magnet, and it's not magnetic. So I don't know if it's a non-magnetic form of iron oxide. But at any rate, we can see the liquid itself is still pretty clear. And I have not noticed any problem in the operation. Everything seems to work just fine. For all I know, this material is making things work better. So I will continue to run the thing and try and learn more about it. But so far I don't see any problems with running with the carbon steel plates other than this red precipitate. So I don't know if it's done precipitating or if more will form. We'll find out. It could have just been from some impurities on the surface of the steel. But I guess we need to learn more. Okay, here's a couple of things that I've learned so far in this experiment. Notice the liquid levels in both the electrolyte and the bubbler. And I'm going to turn on the power at 10 amps. And you see both levels have come up due to the displacement of the bubbles. Now, this is kind of obvious once you see it, and of course all things are obvious once you see it. Another thing is putting aquarium stones in parallel doesn't work. Whatever one has the biggest holes takes all of the flow. There's our production rate at 10 amps. Electrical engineers like to plot voltage versus current curves for electrical components. And so I've plotted amps versus volts for the wet cell. And there's a theoretical voltage of 1.23 volts per cell before any gas production can occur. So for my 9-cell unit, it takes 11.1 volts before any gas can be produced. Now, as I increase the voltage from 0, I did get current. And that is due to the bypass current That's the current going through the holes in the plates, and it's actually a loss. So I labeled this, well, I projected it on and labeled it the loss current. And if you calculate the slope, you get an equivalent of 40 ohms. Now, once you exceed the threshold voltage, the current starts to rise, and you're into the area of producing gas. And as we increase the voltage, the current increases, but this line has a slope to it, and that's, I believe, due to the bubbles displacing electrolyte and raising the series resistance. So where there's a bubble, there's no electrolyte. So there's an increase in the resistance of the electrolyte. At this point, I think we've learned enough to come up with a possible equivalent circuit for our electrolytic cell. This represents the power supply. That's the positive terminal. And as we increase the voltage here, we will get current through our loss resistor, and that's due to the bypass current. Now, the bypass current is much worse in a wet cell than it is in a dry cell. And this is basically the current that travels through the holes in the plates. Then there's also a series resistance, and I'll show you how to calculate that shortly. And then we have a voltage here, which is the voltage that we need to start generating gas. And when we go to zero voltage out here, we don't get current coming back. So that's why I've included a diode there. Now, these resistors here, the bypass resistor and the series resistor, dissipate power and heat up the solution. The power that we have due to the current flowing into that voltage is not a loss to the circuit. This is what's generating the gas. So whatever energy we're putting into that, we would get back when we burn the gas. So that's not really a loss. That's not heating up the electrolyte. But these resistances are heating up the electrolyte. So the total power going into the system is the supply voltage times the supply current. Some of that will be heat in this resistor, some will be heat in that resistor, and some will be energy put into creating the gas. And I'll show you shortly how we calculate that resistor. Now, we just looked at a curve that looked like that, where this is amps and this is volts. And after running all day, I took another curve and found something like this. And I didn't know if the change was due to the contaminants or what. But the next day, after everything had cooled down, I took the curve again and found I was back to this curve. So I'm pretty sure this change was due to the temperature of the electrolyte. So initially I was about 75 degrees Fahrenheit, and later we were about 100 degrees Fahrenheit. So let's look at this curve in more detail and see what we can learn. Okay, this current here is the current that's producing the gas, and this here is our loss current. So the voltage across this resistance is our applied voltage minus our threshold voltage. And then we can use IP and that voltage to calculate the resistance. But of course, the resistance is changing with the amount of gas produced. So note that the gas being produced is directly proportional to our I sub P. So if we neglect I sub L, assume it's fairly small, the gas produced is proportional to the current applied to the cell, which is that current there. Okay, I've added the high temperature curve to the original room temperature curve, and it's getting kind of busy, but I hope you can see what's going on here. This is the original room temperature curve, and the electrolyte was about 75 degrees Fahrenheit when that curve was taken. Then after running for many hours, the electrolyte had gone up to 100 degrees Fahrenheit. So our bypass current increased, so our equivalent bypass resistance was now down to 13 ohms, whereas originally it was about 40 ohms. Now the voltage across the series resistance is the applied voltage minus the threshold voltage. So the series resistance can be calculated as E sub S over I sub P. Now, although the loss current did increase for any given voltage, notice that the current at any particular point went up due to the curve moving to the left. So let's look at these 2 points. On the room temperature curve, our production current was 3.7 amps, and at 0.095 liters per minute per amp, we're producing 0.35 liters per minute. And our watts dissipated is 4.2 amps times the 21 volts. If you follow this down, we're at 21 volts. So out of our power supply, we're drawing 88 watts. Now, after the temperature has gone up, let's look at this point. Here our production current is 5 amps minus 1.4 amps, which is 3.6 amps, which we see is very close to the 3.7 amp point here. So here we're producing 0.34 liters per minute compared to 0.35 liters per minute. And our watts are now at 93 watts compared to our 88 watts. So these points here are very much the same, even though the electrolyte has heated up. So our series resistance has gone down, and that'll help us produce less heat into the electrolyte. Okay, here's a quick review. The current that actually produces the gas, IP, is equal to the terminal current minus the loss current. So IP equals I sub T minus I sub L. And you can, by calculating R sub L, you can then find I sub L at any applied voltage. Now the production rate we've said is directly proportional to the I sub P, or the producing current. And here's some constants that might help you. The production of the hydrogen is 0.007 liters per minute per amp. And of course, the production of oxygen will be at half that volume. So the total HHO per cell, these are per cell numbers, is 0.0105 liters per minute per amp. And since my unit has 9 cells, that's 0.095 liters per minute per amp. Now, if you actually measure the volume of gas produced, there's another thing to consider, and that's water vapor. After going through the bubbler, the gas that you produce is at 100% relative humidity, and the volume of moisture is dependent on the temperature of the water. So if we look at the temperature of the bubbler water, if that water is at 76 degrees Fahrenheit, 3% of the gas going out is water vapor. And you can see how that goes up with temperature. Now, if you want to reduce the amount of water vapor in your gas stream, you could cool the bubbler water. If you bring it down to ice water temperatures, the percent water vapor by volume will be 0.6%. So this is something to think about depending on how you're going to use your gas. Well, here's 2 other facts associated with generating HHO. While measuring voltage versus current, or vice versa, at very low currents, I was seeing big lags in the change in current for a change in voltage. That sort of indicates capacitance. And I did some measurements and found there's essentially (4,000 microfarad capacitor in there. That'll have no effect on DC readings, but it does make measuring currents sluggish at low currents. Here's another fact that may be useful. If you use up a liter of water in your cell, you've generated 2016 liters of HHO. Now that's on room temperature and 1 atmosphere of pressure. If you're above sea level and the barometric pressure changes, this number can go up. Also, if your bubbler's hot and you have a lot of water vapor mixed in, that can go up as high as 8 or 10%. So measuring the volume is not that accurate unless you take all these things into consideration. So, well, the whole premise of this video was whether or not you can use carbon steel plates. And at this point, we still don't know. All I've seen is some discoloration, but everything seems to work fine. So there's some improvements I want to make to my system, and I'll run things for a much longer period of time. And in part 3, then, we'll come up with whether or not this can actually be done. So I hope to see you then.